Okay, today we're doing a compost adjacent math problem. And why am I doing that? Because I want to know how much water I bring in roughly, because I will never know for sure how much actually comes in. But I can try to figure that out with some simple math and with some of the information that I've been tracking and taking note of. So I think I get really excited when I think about how much food scraps come in, but then also the resources that come out of it. And a really valuable resource, which we are learning over and over again through the summers, either wet or dry, is water. And what happens when you throw organics away in the landfill, you have the methane gas that comes off of the organic matter breaking down anaerobically, which is a terrible greenhouse gas. It's not great. It's a terrible situation. We're working on it. But there's also the lost resource of water, which I think is a really interesting aspect. There are ways of collecting the water that comes out of a landfill. I mean, it eventually percolates down through and gets siphoned off, sits in a holding pond, but it is toxic stuff and it has to be treated mechanically before it's actually released back into the environment. So it's costly, either through time or money. The whole mechanical process of it just isn't, it's not the natural way that we should be dealing with the water that is in a circle through our food cycle and our life cycle. So I want to know what we can do better. And so I have the information, and this is just one restaurant, and they take all of their spent coffee grounds and they put them in 5-gallon buckets for me. So they're wet and heavy. A full bucket, when I weigh it, will come out to like 31.5 pounds. And if I want to figure out how much that weighs, like dry versus wet, I don't really have the time or space to just dump out a coffee bucket and let it dry and scoop it back up into a bucket and then reweigh it. So I have access to an old coffee can, like 30 years ago. They put coffee in cans and it was pretty compacted. And that's how the coffee comes to me in these buckets, pretty compacted, because it's wet. It's wet and dense. So I have some notes here that I'm kind of cheating off of as I like write out my display here. But so we have the coffee can coming in at 39 ounces. All right. And it is 6 inches in diameter. It is 6.5 inches high. So the area of a circle, pi r square. So we have pi, radius would be 3 inches. So that's pi 9. And that equals 28.27. So that's the area of our circle up here. So to find the cylindrical area, we multiply 28.27 times the 6.5 inches in depth here. So the area of the coffee can, that is 183.78. Okay, so that is a dense 39 ounce fresh coffee ground can. So the buckets I bring in, see that? Yeah, pretty good. Right, so they are 11 inches in diameter 14 inches tall. This was a bucket that was about 13 inches filled. So there again, we do pi r square. So pi radius would be 5.5 squared. So that's pi times 30.25. And that is actually 95. So we do 95. Multiply that by 13 inches, and that equals 1,235.43. That's a 4. So we then figure out how many times this can goes into this bucket. So we'll do 123.5.43 divided by 183.78, and that will equal out to 6.72 cans. So that's how many cans will fit into this bucket. So now if we multiply 39 ounces by this many cans that fit in this bucket, that comes out to 262 ounces. Divide that by 16 ounces in a pound, we come to 16.375 pounds. So that's how much 16.375 follows me. That's how much dry coffee would fit in this space. So if a bucket comes in and it weighs 31.5 pounds, I don't know how, okay, so if it comes in weighs 31.5, we subtract from that the dry weight, 16.375. That means we have 15.125 pounds of water alone. So if water weighs, we'll say roughly 8 pounds a gallon, divide 15 by 8, we get about 2 gallons of water. Roughly 2 gallons of water. Now, last year I had 6,105.5 pounds of coffee that came in these buckets. The percentage of water here is actually 48%. So 48% of 6,105.5 pounds is 2,000. I'm running out of space. So I had, okay, go back here. 6,105.5 pounds. 48% of that equals, what did I say? 2,930.6 pounds of that is water. We divide that by 8 pounds per gallon. That equals 366 gallons, roughly 366 gallons. So that is, this stuff is all rounded. This is not exact science. I am not a mathematician. This is what made sense to me, so hopefully it makes sense to everyone else. But I think the takeaway here is we are throwing away a lot of water when we don't have to, and we don't have to do it in such an expensive manner. Like if we just took everything and let it happen organically and release back into nature organically instead of mechanically, I think it would benefit all of us so much more. We don't have to worry about the toxic leachate as much. We don't have to worry about the time it takes to actually get it back into Mother Nature. And it's released in the more organic manner of actually evaporating and not being discharged into rivers and whatever other streams or whatnot. So that's my big takeaway. I really want to see how we can do more resource management with organics management, because there's so many more aspects to it than we can even quantify. And it really excites me, and I hope the prospect excites you as well, because this is really cool and interesting stuff, and I hope we can do more of it and do better at it as well. So thanks for watching. I hope my math is right, and I hope you learned something today.